In the name of God, the compassionate, the merciful. Engineering Plasticity, Chapter 4, Constitutive Relations, Part 3. We solved this problem for a block which is under pressure P. These are the X, Y, Z axis, and we have these rigid walls which prevents this block from moving in the Z direction, but it is free to move in the Y direction. Therefore, in the Y direction we have sigma Y is equal to 0, and we have epsilon X and epsilon Y, sigma X and sigma Z, but we have epsilon Z is equal to 0 according to this figure. Now we solve this problem using the Tresca-Yield criteria. Now we are going to use a von Mises material. That means that the material obeys the von Mises Yield criteria. Okay, so the same procedure as before, but using the von Mises Yield criteria. Now if we use the von Mises Yield criteria, considering that sigma Y is equal to 0, our yield criteria becomes like that. And so you can see that sigma XX squared minus sigma XX times sigma ZZ plus sigma ZZ squared equal to Y squared. It's because if you remember, the von Mises yield criteria was like this: sigma XX minus sigma YY to the power of 2 plus sigma YY minus sigma ZZ squared plus sigma ZZ minus sigma YY squared equal to 2Y squared. And then we put sigma YY equal to 0, we get this formula. Now these are the Prandtl-Ross equations that we used before. Okay, we introduced this in the previous slides, so we are going to use them and incorporating the von Mises Yield criteria. Okay, in order to do that, we use a substitution like this: sigma XX equal to minus 2y over root 3 cos theta. Where did we get this? We got this from the diagram. If you remember, we used in the pi plane. Okay, we take the idea from there, so we make a substitution in order to make it easier to solve this problem. So if we use this substitution for sigma XX, and also if we use these identities like sine pi over 6 minus theta, this pi over 6 also we used in the pi plane as well. So we get these expressions, and if I substitute this in here, I will get this sigma ZZ equal to minus 2y over root 3 sine pi over 6 minus theta, using these expressions. Okay, and these expressions, this one and that one, I can get this one. Okay, now we have these Prandtl-Ross equations, and we have these from the Yield criteria. So if I substitute here for sigma XX and sigma ZZ, I will get this equation. Okay, from here you can see that if I substitute for sigma XX here and differentiate, then I get a d theta in here for this one, and of course I have rearranged it, because I've got a sigma xx here, sigma zz here, so I must substitute all of these in order to get that. Okay, so there needs to be some manipulations which I have omitted here, so you have to do the intermediate manipulation yourself. It's easy. So I get a relationship for d epsilon xx in terms of this. Of course I have this d lambda which is unknown. Similarly, I can get a value for d epsilon yy from here. Yeah, from here, if I substitute for sigma xx and sigma zz in here, I can get similar to this one. You can get this one. Okay, and also for the epsilon zz I could get a similar value, but the epsilon zz which is in this direction, z direction, we said that we have rigid walls, so it cannot move, therefore this is equal to 0 as I have put it here. So if we put this equal to 0, we could get the lambda. So that's how we usually get the lambda from these boundary conditions and our main equations. Usually we get the lambda and substitute here so that we get these values. So I get the lambda from here because that's 0 and everything else is known. So that's the lambda, and so I've got this equation for the epsilon xx, and that's the lambda, and I substitute here for the lambda. That I have to do some manipulation. Again, I have not written the intermediate manipulations here. You have to do it yourself. It's longhand. So now I integrate this equation for epsilon xx, and this will give me epsilon xx. Okay, so if I integrate this, as you can see, some parts are constants. That's because we have d theta here, so we have to integrate with respect to theta, and that's what we get here, and we get a constant c. So we have to determine the constant in here as well. Let's have a look. D epsilon zz equal to 0. We had this before. We integrated this. So we have to determine the constant c. Now to determine the constant of integration, consider again the condition at first yield. What does it mean, first yield? First yield is a common point between the elastic and plastic boundary. As soon as the elastic ends, the plastic starts. So that is the boundary between the elastic and plastic. So we call it first yield. Then sigma xx, because we are pushing that way, sigma xx reaches sigma xxy. Okay, reaches the yield strength. When the stress reaches the yield strength, then yielding occurs. Okay. Also, sigma zzy is equal to mu sigma xxy, and so we have here these values. Sigma xxy is equal to y over that value, sigma xx. We obtained this before, except that for this substitution I just put cos theta y, because when this sigma xx reaches sigma xxy, theta reaches the value of the yield, I mean theta changes so that sigma xx reaches sigma xxy, so we call this sigma theta y corresponding to that. Okay, that's a general state of stress, so we put theta here, but that's a specific state of stress which is yield stress, so the corresponding value for theta is this. And therefore sigma xxy is equal to this, so sigma xx is equal to minus 2y over root 3 cos theta. We obtained this when we said that we could solve the Prandtl-Ross equation for the elastic solution, remember, in the previous slides. So if you refer to the previous slide, you can get this. This is easy. Why we using the elastic? Because as I said, the point of yielding, first point, coincides on the boundary of the elastic plastic. So you can use both equations. In fact, if you use the elastic and if you use the plastic relationships, they must give you the same value on that point. So that's why we are using this. We are putting value for the yield, so we get this. And cos theta y, if you put sigma xx equal to this, then you get cos theta y. Okay, and obviously tan theta y, you can get it from cos theta y. Here with epsilon xx sigma yy, sigma xx y times 1 minus mu squared over e. Again, this we obtained it in previous slides. This is just the elastic relationship. This is the elastic relationship, but we have put for sigma xxy. Okay, so that's the point of yielding at yield. It's a yield we have. So if we put this value in here, then everything is known, and I can get C, and C is equal to this. Okay, so you can see here that I have used the boundary conditions on the elastic plastic yield point and obtained the constant of integration. Finding the constant of integration, I just substitute it here and get this value. Okay, so I obtained a relationship for epsilon xx at the first yield. Okay, and this leads to a similar stress-strain curve as for the Trask criterion, only now the limiting value of sigma xs is minus y over 3, which is, that's the difference between the Tresca and Mises criteria. Yeah, this value. In the Tresca it was y over 2, here is y over root 3. So the same curves as we obtained in the previous slide, so I haven't drawn it here again because it's very similar, except the values are different. The trend is the same, and I should mention that as we press this block, at the first we have elastic region. Okay, so if we release the pressure, it will go back to its original shape, because when you press this block, it cannot move in the z direction. It can only move in the y direction and x direction. So when you are in the elastic region and you put the stress, it changes the dimension of the block in the x and y direction. In the x direction, it becomes smaller, the dimension that way, and in the y direction it becomes bigger. But when you release the pressure, it will come back to its original shape. But when you go to the at yield point, yield point, it yields and it will not come back to its original position. Now after the yield point, what happens there? That's where the flow rule comes in, like these Prandtl-Ross equations and other equations, so that they show that how it changes. In here, for instance, if we assume a rigid plastic material, it means that as you increase the stress according to our flow rule, it flows in that direction, in the y direction, and the stress does not increase, remains the same. Okay, so you can get the epsilon xx from here. But if we have a strain hardening, then it would be different. Then the flow rule would be a bit different. As we increase the pressure here, the material flows, but as we increase it more and more, the material flows with more and more difficulty. So we need, as we go further and further, we need more stress to get the same value of strain as before. Yeah. For instance, if you go from sigma y, which is the yield point, to sigma y plus delta y, then you get a certain amount of stress. But if you go as far as 2 delta y, you don't get the a proportional stress, but you get more because it's due to the strain hardening. I will talk about the strain hardening effect later.